If you just do it, it turns out okay. And today, I am with someone who's not a doctor.
Trying to be one. I am doing a PhD, so one day maybe I'll technically be a doctor. got a little bit to go before then, but that's why I like the name Almost a Doctor, because that's what I got called on the radio once by a very, well, at least within Australia, very, very well-known science communicator. And I kind of liked the topic, the title, so I took it made a YouTube channel with it.
So once you get your PhD, you have to change your Twitter and YouTube title.
Yeah, first thing everyone always goes to is what are you going to call it when you do get a PhD? And I'm sitting going, I have no idea. I probably actually will restart my channel, or like restart a new channel when that happens. So I can try and start from scratch with everything I've learnt to that point. And whilst that might set some things back, hopefully it means it's a fresh start. I can make a better go of it the second time around. That's the goal. But I like talking science there, and I'll talk science here. I mean, we got space lasers on today.
Oh yeah. So what are real space lasers? Not the one that the people have up that kill people up in space. Quote.
Oh, well, see, that was what I wanted to try and cover a few different areas today, is because it depends. So a laser itself is fairly well defined, but a space laser is that, say, maybe a ground-based laser that is used for astronomy? I have an example of that. Or is it a laser that is specifically built in space? I have another nice little story about when America tried to basically Death Star in real life.
Like the Star Wars program from the 80s?
Yeah. And when I say Death Star, it was not only called the Star Wars project, but they actually tried to build a nuke-powered laser that was in space. So yes, almost a literal Death Star type weapon, although you wouldn't see the beam because it was X-rays. But yeah, an X-ray laser, which is really weird. But that's partially why they use nukes, but we can get to that. Or there's another theoretical way of interstellar travel, where you basically use lasers as your propulsion source to move craft around. And those lasers can be based elsewhere, so like on the moon or on other planets, etc. And that would give you a little highway of lasers if you really wanted to go full on with that. Though there are some problems with that method, which I'm happy to cover. So yeah, there's a lot of different things.
A lot of different things. So
yeah, see how many we get to.
First of all, let's tell the people that might not know, what is a laser?
Okay, so a laser produces what is known as a monochromatic coherent beam of light. Now, break that down. Monochromatic, mono meaning one, chroma referring to color, so it's a single color. Now, when you look at, say, the electromagnetic spectrum, so we're used to seeing the visible parts. It's kind of like the rainbow section in the middle, and then you've got infrared, micro, and then radio going to longer wavelengths, or you can go UV, X-rays, gamma rays going shorter. You can't have a single wavelength. It's just mathematically and from quantum mechanics impossible. But so what they do is they just define as being very, very narrow. So to us, it will always appear as one color. So hence, monochromatic, one color. Coherent, it gets a little more confusing, but because light, is both a wave and a particle, if we're thinking of the wave part, it just means that the waves line up with each other in space. So spatially and temporally they're matched, because the way a laser works is you build what's known as a cavity, and you bounce light back and forward, and you give it time to kind of build up, and then you leak part of that out. And the way lasers work, you have one photon come in, you're pumping a lot of energy in to do it, and then you generate a second identical photon and they go out, and you keep doing that back and forward until you have lots and lots of light, and then the beam comes out the end. And there's a few different ways you can do that. I won't get too much into it because it's very technical. And but yes, it's a narrow focused beam of one color, and that kind of makes sense if you think of laser pointers, like red pointers, green pointers, etc. They're always one color. So anyone who tries to show you a white laser or have a multicolored laser in a movie, that's not a laser. They don't work that way.
So like the lasers, so probably I remember lasers probably don't work the way in the movies, but But there's probably no, or is there lasers in like movies that can kill you, like James Bond, old-fashioned James Bond lasers?
No, lasers are a horrible weapon, because everyone they would, I guess, fall into directed energy weapons. They're terrible for that because lasers are inherently inefficient, so they're a big power waster. They have uses, but as a weapon, you're much better just getting that energy to propel a solid object. If you've got a laser that has enough power to cut through, say, an enemy's craft, because we're talking spaceships, you've got enough energy to just fire a solid object at them, which is going to do far more damage.
Yeah.
Like, everyone talks about fancy space weapons in sci-fi movies, but the most effective weapon.
Yeah, so no Star Trek lasers anytime soon or ever.
Yeah, and even these kind of like phasers, I know they call them phasers, they try and go up other things, but still, yeah, your best weapon in space is just to launch a heavy rock to a heavy object at the enemy. And in space, yes, if they have enough warning, they can try and get away from it. But if they get hit by it, there's nothing they can do. It doesn't need to be that big.
So
the speed at which things move.
Yeah. So speaking of lasers, space, how can lasers be used for travel in space?
So the brilliant thing about light is it doesn't need a medium to travel in. So photons just travel, and so it's just light. It's like I can shine a torch through space, and it's just. So light has two components to it. You've got the electric and the magnetic components, which is why it's called electromagnetic radiation. Now, it can't exist without one, so you can't take away one and still left the other. And it's not like a magnet that you can manipulate with another magnet. It's kind of almost self-contained. So you've got these little photons. It gets confusing because quantum mechanics kind of tells us it's both a particle and a wave, and it behaves as both. So you have the little photons of light, which is just a packet of energy, and they'll just move on their own. I guess you can think of it as an analogy to throwing a rock through space. The rock's just going to travel until it hits something. The light is basically, or at least the energy is going to travel until it hits something. You do get to a limit at which you won't ever be able to see the light. So if we actually fast forward this galaxy 1 trillion years, you wouldn't actually be able to tell there was a Big Bang at all because we wouldn't be able to see any other galaxies. Only our galaxy would be visible to us. And so the history of the universe would basically disappear without something being there to record it, though we're definitely not going to be here in 1 trillion years, or at least definitely not on this planet. We've got about 1 billion years before our sun starts to get too hot for us. But that's
hopefully some of our descendants might make it that long.
Yeah, maybe. They'll look very different.
Might evolve into it by that point.
Yes. Well, I don't think that's something at least we need to worry about. That's at least one example of a problem we can say that can be solved at a later time, and we're not exaggerating, unlike a lot of current problems that probably should be solved.
Now you said, but lasers can be used for communications.
Yes, lasers are used actually fairly common for, like, a lot for communications. You can actually a lot of fiber optics communications that's done by lasers. So the typical wavelengths tend to be around 1550 nanometers, which is infrared. So it's invisible to our eyes, but detectors are there. And here's the thing with lasers is that the longer the wavelength, so in the visible, that's redder colors, so lower frequencies, are more efficient. The shorter the wavelength, and this is not anything to do with technology, it's just part of physics, they get more inefficient as they get bluer, so going the other way. So it's actually fairly more efficient to make an infrared laser than it is to make a red, a green, or a blue laser, which is why most lasers tend to be green or red. Making a blue laser is hard, but also our eyes are more sensitive to green light, so that's why the green lasers seem more powerful. But so red lasers are easy to make.
So lasers are more on the infrared side, not the ultraviolet side, then?
Yeah, you're more, or at least they're much easier to build on that side, and yeah, they're not as power hungry for the same output. And so a lot of communication ones use lasers, and then you can encode a lot of information. You basically can if you've got a diode laser, they're really easy. You just change the current going into it and you change the wavelength and the power coming out. So you can basically have little fluctuations in that laser that can impart information just like you would a radio signal or picking up the internet from a receiver, except it goes through a fiber optic. And you can also, and this is something I've heard used as well, you could also use them as like just direct fire a laser at a detector over a distance as well. The fiber optic basically gives you a nice channel so you can bend it through stuff. Then you're not worried about direct line of sight. They're also good for like if you want to align things, so you want to know distances. I know in Europe and probably elsewhere they've used it to actually help build underground tunnels, so like rail tunnels, because you can have a bunch of lasers pointing to each other to help align the tunnel and know exactly where you're going. So there's a lot of things you can do. They're really cool. Can you make a microwave laser? Yes, the first so
You frozen? I think he's frozen. Okay. Australian internet, or my internet. I'm not sure which one it is.
Are we? Sorry, the weather recently has been playing with the internet. So sorry if I drop out. I'm trying to get around problems, but there's only so much.
I wasn't sure. I was for a while. I was sure if you were in deep thought or you're frozen.
Frozen generally. My brain likes to race a bit. So sorry to answer Titan's question, and welcome Titan, the second show he's watching me for today, which is nice. Yes, in fact, they're known as masers. So a laser stands for light amplification by the stimulated emission of radiation. So the light part refers to visible light, and so you change that out for microwave, so you get microwave, etc., etc. And so you get lasers, masers. You can get Zasers if it's X-rays, though we tend to just further. And microwaves came first. They built microwave lasers first, and then when they made the first visible laser, which was using ruby crystals in 1960, I think, if I get it correct, they actually referred to them as optical masers before laser took off. So it was. So yeah, it's actually really easy and easier to do so. I think you could. I'm not sure how easy it'd be to make a radio laser. I'm sure you can do it. You're not going to be doing it chemically. So a lot of lasers are done using colors, basically, in molecules. So you would have trouble doing that in radio because you can't find anything. But I can't see why not.
What about lasers? As I've heard, like we're seeing like lasers used in like surgeries now or in doctors.
Yeah, so they're actually depending on exactly what you want to do, is that they can be cleaner than a scalpel. And so lasers, although we might like to think of them as a beam that's perfectly kind of like parallel, it just keeps going straight, they don't. They do diverge. They'll spread out eventually. It's just a lot slower than, say, a regular light bulb or an LED or something, because LEDs are also monochromatic, but they're not focused like a laser is. But you can also put a lens in front of a laser and focus it. Or so that's how like laser cutters work. They will focus it and have that focal point where you're cutting. You can do that in surgery. You can have lasers that can help cut. So you can do that for even cutting out tumors now. It's still fairly new, and its uses are still being developed, but you can do that for a lot of things. You can also use water for surgery. You can use a water jet because it doesn't rip cells apart. In that case, it just kind of pushes them apart, so you get less damage. So there's a lot of cool things you can do in.
I can't remember it wrong, but I think my friend had like laser surgery for his eyes.
Yes, that one's basically where they use the laser to do. I think they do cutting with it. It's getting more into medicine than I normally deal with, but it's not an ideal procedure because it can make it really hard later to do other things. So if you want to say remove cataracts, you've had laser surgery, I think there might be issues, but don't quote me because that's going, as I said, into the medicine side, which is not my area of expertise. But you can use what's known as a cold laser in certain medical treatments. That doesn't actually mean the laser is cold. It just means it's not hot enough to burn skin, and you can use it for, say, like hair removal, etc., or other dermatological treatments. So there's a lot you can do with lasers, and a wavelength, so the color will change what you can do. But as I said, they tend to be more of a tool rather than a weapon or something that's particularly good at doing significant amounts of damage. I mean, in theory, yes, I guess you could use lasers for weather control, but you would need a very, very oversized, very overpowered laser, and I guess you could heat areas of the Earth and do it that way. I can think of much easier ways to control the weather than that, which I think says a lot because we're talking about weather manipulation.
Be like, I know how to control the weather. All right. So you also mentioned lasers can be used for astronomy and stuff.
Yes. So one of the areas that, and I've actually done a mini project for this when I was back in undergrad, we were looking at ways to do it, is you can use them in a number of ways. One of the ones I wanted to go with is in an area known as adaptive optics. So one of the big problems in astronomy in terms of ground-based telescopes, so Hubble is space-based and it's outside the atmosphere. One of the problems is with ground-based astronomy is the atmosphere. When you see stars twinkling, stars aren't actually twinkling. It's our atmosphere. So when you look on a hot day at, say, like a road, and you can see the heat waves coming off it, and you kind of get those like mirage effects from the hot air rising, or even if you just heat a pan and watch it. Our atmosphere is doing that all the time. And unlike, say, hot day where you're only looking a couple of 100 meters, you're looking several kilometers through fairly thick atmosphere. And this is if it's a clear sky without pollution. And so the atmosphere is causing all these weird waves everywhere. So you can build the biggest telescope that has the best resolution on Earth because it's much easier than trying to put the same thing in orbit. You can have a lens that's hundreds of meters across. Good luck getting that into space, though. And this was but the problem is the atmosphere still limits. So you need to be able to know, but if you could actually know what those waves were, you could potentially account for them. If you knew what the distortion was, you can correct for it. So you can work backwards. So one of the things they do is, well, let's actually get a really powerful laser and attach it to our telescope and fire it near the object we're looking at. So you fire the laser up through the atmosphere and you put it next to the star. It's far enough away that it's not kind of blotting out any of the light from the star. But you know what that laser should look like because it's got to be a straight, flat beam. And any distortions on the spot that you're seeing from the laser has to be because of the atmosphere. And so you can figure out what those distortions are, and then you can correct for it. And then you can hopefully have a much clearer look at the star as though the atmosphere wasn't there causing problems. So you basically fire a laser into space because they even refer to them as like artificial stars. You basically generate an ideal spot because we know what lasers, like a laser spot, would look like if you in a spectrophotometer. We know what it will look like.
So lasers can help us see clearer in space then?
Yeah. And you can actually, I'll see if I can find an image to show of this, but it's a lot of the new, or at least some of the new light based telescopes that they're building have really powerful lasers built into them to do that.
Can we see further than we could before?
Yeah, theoretically, because if the atmosphere is what's blurry and it's stopping us getting a better look at something in the distance, but we can essentially correct for that, yes. And it also means that it helped reduce the need for space-based telescope. So James Webb was it's the recent one that got a lot of attention. Hubble is the go-to famous example before that. They're limited in size because they're still a satellite. Yes, they're both pretty damn big, but they're nowhere near the size of what you could have on the ground. And radio astronomy is a good one because you're not as worried by the atmosphere. In that case, you can have radio telescopes that are hundreds of meters across. And the biggest one, I think, built or at least planned was 500 meters across. And then you had the one they had in GoldenEye, which was a real telescope, although you're not sending signals with it, which is I think it's the 300 meter array, because it was 300 meters across. But the problem is if you try doing that visible, can't do that from Earth. So it's really cool. I'm going to see if I can find a nice image to share. So yeah, it's the fancy field of adaptive optics, and what you do is if you know what to make these corrections, you basically make a mirror that can wave as well. So if the atmosphere's got distortions, you distort the mirror. And if you ever think of like looking at curved mirrors and how it distorts the light, you basically do it to counter whatever change there is. It's really, really cool, but it's basically where the mirror itself is not smooth, but the image you see off it is exactly what you like, the exact perfect image in an ideal world, obviously.
So why, if lasers can be good, laser telescopes can be good on the ground, how come why are they in space then?
Because it's still not a perfect system. It's still, fairly early on. I do have an image. Let me get that ready. So and it's not.
And I think he's frozen again. Come on, internet. Come on down. Oh, yeah, it's a picture at least. Maybe. That we can't see right now. Let's wait for him to return after these messages. So how y'all doing in chat? Oh, he's gone now. All right. So how y'all doing while we wait for him to get back? Hopefully. Advertise. Well, next week, VB will be on the channel talking about Henry VII. So looking forward for that.
Sorry, I've been trying everything to stop this, but unfortunately, I'm somewhat limited and don't have unlimited options.
Yeah, want to use laser for better internet quality access?
Well, we're meant to be doing that, and it still doesn't quite work as well as we'd like. Oh well. But sorry, what point did I cut off? Sorry?
You start showing a picture.
Oh, yes. I was going to try and show you the sort of things it's meant to. So it's quite cool. They look like, see if that should work. So these are what they sort of do. As I said, you basically just attach a giant laser to a telescope and you fire it to make an artificial star. And sometimes you can do it from multiple points. So this image is a little small, but if we zoom in a bit, you can see that you've got kind of like 4 lasers. So you get 4 artificial stars around it. And there are examples. So you can do like this one here. You can see that you get a better resolution using this without actually having to make a bigger lens, because in optics, the bigger the lens, the better the resolution, so the more detail you can see. So the human eye, the lens is what is roughly, if our eyes are actually working properly, roughly what determines the resolution that we can see. So if you want to enhance human eyesight, then you need to actually give us bigger eyes. And that's what what you're trying to do with telescopes. But I said the atmosphere is quite a limit. But you can see with some of these advanced optics that it does a pretty good job. And this is probably what I quite like, this idea. If we want to see things like exoplanets there and see farther detail, or see to the furthest reaches of the universe, or our local universe at least, in any resolution, this is probably my pick for how to do it. Because we're limited in how easy it is to put a big telescope in space, because, well, it's putting something in space. Also, this is probably going to be a bit confusing to people, but you can see the mirror. So the adaptive mirror actually moves and wobbles with the wobbles of the atmosphere, but you need to know what those are, which is where the lasers come in. So there. Sorry, hopefully that was interesting to people. I've done a bit of work with it. My group actually works in trying to develop those detectors to pick up what those distortions are, and there are probably ways to do it without a laser, but lasers are a cool way to do it.
So the lasers reflect the mirrors and not burn right through them?
So they're not going to. So most lasers don't burn through things. Even there's a lot of powerful lasers that are super intense, that'll do damage to your eyes but aren't going to burn, because, as I said, they're really, really not a good thing for a weapon. You wouldn't use a laser to try and kill someone. It's the worst way to do it. They're good at aiming things. They're good at, but they have the uses, but they're not good for transferring energy. You lose. Okay. There's much better ways.
You mentioned lasers can be used for communications. How fast are they?
The speed of light. So there'll be a slight slowdown because you're actually traveling through a media. If you're in space, it's essentially a vacuum. So it's pretty much 3 times 10 to the 8 meters per second. It's basically fast enough to go around the Earth 6-7 times in 1 second. It still takes about I think it's 11 minutes. I'll double check to go from the sun to here, and it's roughly 20-minute round. It's 20 minutes either one way or round trip to Mars. But that's the fastest you can actually send information. The speed of light is the fastest you can transfer information through the universe, according to all of the nice, lovely laws that we know of. So that's the way to do it.
So hopefully someday we will have internet lasers that can have this lag quality we have today.
The big problems isn't that we can't do that, because we're already doing that. Fiber optics, like undersea fiber optics, are done by a laser. The problem is the bits, what happens at the end of that laser. That's where we're having all our trouble, because sometimes it's got to be converted to a tower and sent as a signal, or you've got people who you got the fiber optic almost to the house, and then you switch it over. That's the whole thing of, people may have heard of copper to the node. It's like, then we switch it back to the old fashioned slow method for the last bit and just ruin the whole purpose of putting in fiber optics. It's brilliant, but it's
I recently got fiber optics in my internet house, so it's a little better quality, and I had the cable lines.
Yeah, and they use lasers, which is cool. Nice. Yeah, I want to see how that goes. But
now, you mentioned back before the Star Wars program, you had nuclear lasers.
Yes. So, bit of background. As I mentioned earlier, the shorter the wavelength, so if we're thinking visible bluer colors, are inherently more inefficient. So they become harder and harder to make, because the power requirements keep going up and up and up. And it's not I half the frequency and I double the power. It's the factor is F cubed. So it's whatever the change is with a power of 3 on it. That inefficiency goes up. So if you're going from, say, a red laser to an X-ray laser, at least the wavelengths they're trying to look at, you're looking at for the same number of photons, the same energy output, roughly the same energy output, sort of changing the wavelength, you're looking at about 1,000,000-fold increase in required power. So if you want to actually build a powerful X-ray laser, which is what America wanted to do back in their Star Wars project during the Cold War, it was in the Reagan era.
Yeah.
One of the problems was that there wasn't really an easy power source that anyone knew of that could make an X-ray laser. What they wanted to do with it was be able to fire them at incoming nukes. So at that time, it was Soviet nukes.
And destroy
And
them?
and basically destroy them mid-flight while they're still in the atmosphere. But
that wasn't probably physically possible.
No, not really. Or at least, so it was like, so we need a really powerful energy source. And someone said, well, we could do it if we had what was known as an X-ray flash. So if we can have something that produces a very high amount of X-rays, not even as a laser, but just an insane amount of them, we could probably direct some of that and turn it into a laser. You build, I remember I mentioned earlier, is a cavity and you bounce the light back and forth. You basically make an open cavity, so it makes a one-way trip, which is also one of the reasons that X-ray lasers becomes really hard, is that X-rays are almost impossible to reflect. You can't easily make X-ray mirrors, which if you're dealing with light, you can bounce it back and forth and let that beam get really strong. Can't do that. So not only do you have all this extra energy you need, but you need even more energy because you only have one shot. So they're like, we need a lot of X-rays. And then someone subtly kind of hinted that an X-ray flash, and then people kind of got the idea that the only thing at the time that could do that was a nuke. It was literally, what's the most powerful thing we can think of? We'll do this.
Destroy nuclear with nuclear, basically. Fire.
Yes. So they're like, nuclear bombs produce a lot of ionizing radiation and X-rays. Why don't we try harvesting some of that, like harnessing some of that and using that as essentially a directed energy beam that can destroy them? So the idea was that you would actually have a nuke with up to 50 of these lasers attached to it, and they'd point in different directions, so you could target 50 incoming nukes at once. That was the dream. It's the second video I made on my channel. It's the most popular, but it's also the second one, so it's a bit trash.
And that wasn't physically possible.
They did it.
Okay.
Sort of. So it was never tested in space, but what they wanted to do is, this was in the era where they started to realize testing nuclear bombs on the surface was starting to, surprising to apparently everyone except those who actually knew what they were doing, which should have been a lot more people, that setting off, nukes everywhere was not good for the planet in terms of releasing radiation. So they decided to do the tests underground, where you literally bury the bomb and set it off. And then you can see there's a lot of nice video footage. You can even find it on YouTube of underground tests. And so they ran these tests that way. Sorry?
I got to make a joke. It says, well, what setting up bombs everywhere wasn't a good idea. What about the old duck and cover commercials?
Yes, because that's how you're going to survive a nuclear bomb. Just duck under the desk. It depends how far you out. How far out you are. It actually may help from the initial blast.
Okay.
If you're far enough away, it will increase. Like, I know in warfare during an artillery attack, just lying down on the ground increases your chance of surviving by about 10-fold.
Okay.
At least sort of World War II
So it wasn't completely bullshit. It was some to it.
No, there was a little bit to it. It's better than standing up and watching it. But it's not, if you're next to the epicenter, it doesn't matter what you do. But if you're further out, it'll probably help you. But then you'll want to get away very quickly from the radiation and get cleaned from that, which is the harder bit. Unless it's a hydrogen bomb, then there's less radiation. There's still some, but that thing's more powerful anyway. So basically just don't be near nuke when it goes off.
A much wider boom.
Yes, you basically use a mini nuclear bomb to start a fusion reactor, which is what the sun does, and then use that to make a really big bomb. You can look up the Tsar Bomba, which was the biggest bomb humanity's ever detonated, where Russia made. So the Hiroshima bomb was 16 kilotons. So it's kilotons of like the equivalent volume of TNT. So it's 16,000 tons of
and that was like the weakest
TNT.
of all nuclear bombs. the first atomic bomb, like
Yeah.
the weakest.
So that's 16 kilotons, so 16,000. The Tsar Bomba was 50 megatons, so 50 million. And it could have been 100, but the scientists were actually scared of setting the atmosphere on fire. So they scaled it back by half, and it's still the biggest bomb that was ever dropped. I guess you could, enough nuclear bombs detonations could change the orbit of the Earth, because it's, you know, momentum has to be conserved. You could push the planet a bit with them. I'm not sure exactly how much you would need. Good one, but I mean, if you think about, they often talk about asteroid impacts in terms of having a nuclear bomb equivalent in terms of how much energy they impart. So yeah, you just need a lot of them to do noticeable difference, and you're probably going to end up putting us into a nuclear winter, but well before it'll be the disruption to our orbit that does damage.
Well, before he gets that, he has to get this done first.
I wish. The problem, though, is, as I said, lasers do diverge slowly. So if you're firing it from Earth, they're not going to be actually particularly narrow by the time they hit the moon. So theoretically, with enough power, yes, you might be able to, but you're not going to generate enough power to do that. So yes, in theory, you could write your initials on the moon. I wish I could do that. That'd be cool. Just almost a doctor was here. Wasn't here.
Yes. So what other things can lasers do that we haven't talked about yet?
Well, you can use them for medicine. You can use them for space. The other one you can do is space travel, interstellar travel. And you might be thinking, how would you do that? Well, light is really cool, because even though photons don't have what's known as a rest mass, they can still push objects. They don't weigh anything, but they can push. And if you
as a propulsion device,
yes, you can use it as a propulsion device. So you can, I think it's photon pressure, and you can also use the fact that light has momentum to build tractor beams. I've actually done it with a small red laser. You can grab tiny objects and move them around. I did that in undergrad. There's a little lab setup you can do. It's amazing. They're known as optical tweezers, and they're essentially a tractor beam. It's harder to do it for like the sci-fi Star Wars style tractor beams that can grab an entire ship, but you can definitely do it on the small scale. And because you can push things with light, one of the ideas for interstellar travel is you build a solar sail, which is just a big light, object like a parachute in front of your craft that reflects light, and then you fire a laser at it, and the light pushes on the solar sail, and because it's been reflected, the momentum must be conserved, so the craft gets pushed forward. And they reckon you can go up to, I think I've heard some sources that talk about 0.3 C. So C is the speed of light, so 30% the speed of light, though I think 10% is another number I've heard, which seems a bit more reasonable to me, which for non sort of like warp drive style travel is insanely fast.
Yeah. How fast does this feel like compared to the speed of sound that we have now on Earth?
So speed of sound is about 300 meters per second, give or take. There's a lot of variables, but speed of sound needs a medium. So in our atmosphere, that is, you can go up to like thousands in solid objects, but we'll talk about our atmosphere because that's what we always refer to it as. So it's about 300 meters per second. Speed of light is 3 times 10 to the 8. So it's 10 to the 6. So it's about 10,000, no, 100,000 times
faster.
Yeah, I think if I've Sorry, it's a bit. I'm trying to do the maths in my head, which I'm never good at. I like to write things down, but it's a good number of orders of magnitude faster. So yeah, it's not a close comparison by anything. So
the
10%
solar,
the speed of light.
So the laser solar flare will be definitely faster than any plane we can have on Earth.
Oh yeah,
even at a third of the speed of light. Even at
the
third.
Yes, the fastest object humanity has ever ever built was the recent Parker Solar Probe, which went through the corona of the sun, and its top speed was an insane 700,000 kilometers an hour. And this thing would still be several orders of magnitude faster. It would be I think this thing would be like 300,000. No, more than that. So 700,000 kilometers an hour. This would be 300 million or something. Doing the maths in my head, it would still be several orders of magnitude faster than the fastest object, just as a comparison. I do think there's a bit of a problem with that, is that, as I said, lasers spread out. So once you start to get far away from the source it's pushing, because you'd base the laser on the planet and fire it at the craft. Otherwise, momentum means you'll never go anywhere.
Like, would you slow down eventually, or would it be that, and that once the object in motion stays in motion, it will keep going until
it will, but it means you won't have an easy way to change direction without using like the slingshot effect, so that you use planets to bend around. So it would be good for accelerating and for shorter trips, but also you get to the other side of it and you have no way of slowing down, if that's your only
or a way of coming back.
Yes. So it might be good for, say, around a solar system. I've heard people talk about it, and I've chatted with a few people in Twitter DM conversation about how you would set it up, and you could potentially do it as within the solar system, so moving between planets. So you put a couple of lasers on each planet, and then you can send craft back and forward that way, and that would be at least a cool.
So I think the furthest planet, because the further planets are like gas planets come on anyways. Like say how far would it take us to get to, like, say, a moon on one of the Saturn moons using that laser thing?
Sorry, couldn't quite catch all of that. I think the internet.
Sorry, how using like the laser things? How fast would it take to get to a Saturn moon?
Oh, I'm not actually sure. It would depend how fast it's accelerated. It would probably be quicker than our current trips to the moon. You'd be doing it very, very quickly. 0.1c. I'm trying to do a lot of calculations, but there's so many variables that my brain is not quite happy.
Paper.
Well, there's also it depends on the acceleration, which I don't know. I don't know how fast it would get you to 0.1c. It would be fairly quick, but also it couldn't be too quick that you killed everyone.
Yeah.
It would probably be on the order of days, whereas at the moment it would probably a trip to Mars is about 1.5 years. So you could do this or at least in weeks, depending on. I think you'd take longer by the time you're getting to Pluto, but even getting to Pluto, I think, would be faster than our current rockets getting you to Mars. For comparison,
it would take a year to get to Mars with our current speed.
Yeah, it's about 1.5 years because our rockets are pretty slow. They're fast for what we've made so far. They're just slow in terms of
plus you got
the distances that we need to travel.
The difference. Plus you got to count out for the aiming it right, or you.
Yeah, aiming it's probably the easy part, though. At least lasers are easy to aim because you know where they're going. Particularly in space, there's nothing to deflect the beam. I mean, gravity will have a small effect, but within our solar system, it's going to be so minor that it's either easy to correct for or you don't even need to.
So, but basically, it won't be a laser speed. It probably won't be like that's still kind of slow in space, but still going different planets won't be like a a multi-year generational time you get back, you have grandkids thing.
Yeah, at least within our solar system, you could do that. It would still probably be a generational thing, or at least close to it, to go to other star systems. Though it's not a particularly quick thing, and I think it's faster, so you could do it in under 100 years. I think to our closest star system at the because it depends. It's still theoretical, so the exact speeds would probably vary. And I said, one of the problems is that it's very one way, which is not useful for
Yeah,
first trips.
yeah. So
You could
you
do
better
it,
have
and you could send probes.
yeah. So you
You
better
probably
once
wouldn't
you
want to send people.
get that's probably once you get there, you better have enough to build a laser to send you back to Earth. Then if you want to go
Yeah,
back. Otherwise, you
is,
building better have a family start building your colonies there.
yeah, and there are ways of doing it so that you fire it so that it like launch your object in a way that it will fall into orbit of the other planet. So you kind of get pulled in by the gravity, but that's still not particularly easy without the ability to propel yourself, or at least change your direction a bit. But it's possible, but these things get very, very complicated very quickly because there's so many factors involved that it's. And so the people who do the calculations are people who are more familiar with astronomy and the maths involved here than I am. That's why I said there's too many unknowns in my head to be able to even give you years.
It's almost like different people have different knowledge and science skills.
Yes, it's almost as if that's how that works, and it's so narrow that no one can pretend to be an expert in. Well, I mean, no one can be an expert in anything, though. I guess a lot of people do pretend to be experts in all science, which is annoying because it's. I like my lasers. I do a lot with it, and my area is spectroscopy. But I can't tell you how to calculate the trajectory of our next rocket or our next satellite to Mars. I couldn't do that. Probably just as much as the person who can do that couldn't do my PhD, because that's not their area, and no one.
You're not going to look something by on geology or biology anytime.
Yeah, my favorite image is the bird one. It's like biology to a physicist, and it's a bird with all the labels, the bits of its anatomy, and every single one of them just says bird. It's like to put the beak, the eye, the wing, all the bits and pieces, just bird, 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 bird. Or the other one, which is like bird, 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 flappy bit, bird, bird, beak, bird, 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 bird. Because it's as much of a joke as it is, that's how it often goes. It's like I'm not a biologist. I don't pretend to be. I have fascination for kind of like the paleontology side of it, but that's a fascination, and I learn it more as a hobby. I'm not an expert.
Speaking of that, could lasers be used to find bones and stuff underground?
Lasers can be used to map fossils once you've found them. If you wanted to render 3D images, one of the and so you could do that, but it's not going to find them. You're not the lasers we've got.
Okay.
Maybe there's a way I'm not aware of, but I can't think of any. There's much better ways to do it. At this stage, the geologists have more efficient, more appropriate methods. One of the cool ways lasers have been used, and this has been going for a little while, as I said, because they are really good at mapping 3D surfaces. So you fire a laser and it basically scans the shape of something. You can use them, as I said, for bones, but if you want to switch to archaeology for a bit, I know a good example of where this was used was in looking at some of the the older Mayan and Olmec pictograms and artwork they found carved in stone, where the paint and the carvings has faded a lot over time. You render a really, really complex, like a really high detailed 3D map of this carving, and then you can use the computer to enhance it, and you can basically reconstruct what it actually looks like. So what to our eyes is not a clear image, using the laser in a computer program, you can see what it originally looked like, and that's really cool. and you can use similar technology for mapping things. So if you want to use light for doing those sorts of mapping things, LiDAR is a really good example. And one of the places they've used that is also mapping or trying to find all of the old Mayan cities in Guatemala and Central America. And when they did that, they finally got a map of what basically they removed the forest and they could see the ground and you could see where cities were because you could see the bumps that are left over in the middle of a forest where you could walk 100 meters, like past it within 100 meters and never know you just walked past a city. But with LiDAR, you could spot entire. And they recently figured out that their initial estimates for how many people were probably living there was 10 times too small. They found so many more settlements that were so much bigger than they thought that there was a lot more people there at one point in time. It's quite fascinating. And so you can't see through ground, but
okay,
you can see other things that otherwise aren't so obvious. So if that's hopefully that adds something there. It's not as so it's not you can't see in the ground, but you can other cool things. I like it.
So what are you getting your PhD in?
So I'm in physics, and my PhD is on building, or hopefully if it works out, we're building and developing gas detectors for environmental monitoring. So our goal is to make small, lightweight, but super accurate detectors that can be attached to mobile remote control vehicles such as drones, so that we can map the environmental impact of the release of greenhouse gases such as methane off things like landfill, waste processing plants, because at this stage we don't really know how much is coming off, and methane is 21 times worse as a greenhouse gas than CO2. So if we're going to do like carbon, work towards carbon neutral technologies and or try and reduce the methane, we need to know how much methane is actually there. And whilst we have detectors for it, they're not suitable for mapping large areas with any degree of accuracy because changes in the wind.
So not only our
useful.
carbon footprint, but our methane footprint too.
Well, methane can be counted as carbon footprint, I think, in terms of greenhouse gases. But yeah, you would map, not just CO2, you'd map other greenhouse gases. And we need to know if we know what that footprint is, or we can do it. But also you can try different methods of storing or handling waste or agriculture and see how that affects the methane. So you can figure out what the cleanest ways of doing things are. And if you can detect methane in the concentrations we want to look at, you can also do it to keep people safe in confined spaces. If I can detect methane in parts per million concentration, I can detect it well before it gets dangerous. And I can map areas, so you can potentially build better safety devices too with it. And so I use lasers to basically generate sound waves out of methane.
That's the question. That's
I make
the next
it
question.
sing.
How does that affect the lasers at all, or is that totally separate subject?
No, it uses lasers, and so the laser puts energy into the methane, and I wobble the laser and basically make the methane sing. And the more methane there is, the louder that song will be, the louder that chorus. And we pick it up with really, really fancy, sensitive microphones.
Like the next hit single chorus song.
Yes. We're basically putting greenhouse gases on the American Idol or The Voice or something. I don't think they'll turn too many judges' heads, but oh well. They might save the planet. Or help us save the planet, at least.
So what does it sound? What does it sound like? Anything in particular? Or just...
So if you're using a sound frequency that's audible to the human ear, it's a single tone, but they're very quiet. You're not like our ears, I don't think, are sensitive enough to pick up at least the sound waves I'm producing with the concentrations we've got. You're not going to be able to hear it. It's too quiet. That's why we need fancy microphones for it. Some of the frequencies that are used, the more common ones, are too high for us to hear as well. But you could theoretically, at the frequencies we're dealing with, if you upped the concentration and the laser power enough, you would hear it as a tone. It's within, the one I'm doing at the moment is within our range, but it would be, when a computer plays a single tone and then it stops, something like it, that's what it would sound like. It wouldn't be a song or anything. But it's quite cool. But it's very difficult. There's a lot of, it's not an easy thing to get working for what we want, but we're trying. Well, I'm trying. It's my PhD.
So, are you anybody else in your team, or just you solo on this?
I do work as part of a team, but this is my project within the team. So okay. I work on this, and it's my job to do it. But I've got people like my supervisor and other postdocs. So postdoctorate, so people who are working as an academic, but they're not yet a professor or like the supervisor level. They have a PhD and they're just working alongside me, and I can go to them for advice. But it's sort of within my group, at least, it's my little. This is my little project.
So are you like to have like a theory named after this laser yet, or you're not there yet, or a hypothesis for this laser?
So this technology is known as, the one I'm doing specifically is known as KEPAS, Quartz Enhanced Photoacoustic Spectroscopy. Don't worry about it. It's just fancy. It gets very complicated, but that has been around for a while now. Other people have done it. I've now got it working so that I can actually detect methane. The hard part is actually getting it so that it's suitable for our purposes. So actually being able to detect lower concentrations and to do it quickly, that's the hard bit. So basically faster to resolve and higher sensitivity is what we need, and that's what I'm trying to do at the moment. So it bounces back and forth, but hopefully we can get somewhere cool with it.
So this is like measure how much we have or prevent it?
Yeah.
Or
so it'll pick up whether it's there and then how much there is around. That's the goal. So because I said it
won't lower it won't kill the greenhouse gases or anything.
No. But again, if we want to solve these sorts of problems, we need to know what's going on so we can deal with it. So it's useful in that regard. It's not, and this is again when you mentioned earlier, it's as no scientists have their own areas. It's not an expert in everything. It's exactly, this is my little area, and that plays into someone else's area. So I get some information, then someone else can take it a bit further, and before long you have this nice long interconnected kind of chain of different technologies and different people who have got these new processes that one day may improve
it's not like
the planet.
Different things, but also like different things build up on each other.
Yeah, and it's not just a tower. It's kind of, I think it more of like linear this way because it can go back and forward. Okay. And what I can do can help someone else, and what they can do in return can help me. And it goes back and forward. It's not, science is not some isolated process about a genius in a lab who suddenly one day comes up with a eureka moment, writes it down quickly, and then builds a prototype in a couple of days. I think the movie idea of science is not how it occurs at all. The actual process is fairly boring. The findings when you get to the end are interesting, and it's very rewarding, but it's the actual process is very slow, very tedious. Very methodical, and not something easy to put into movies without putting.
And that's even if your finding to affect you in your lifetime. A lot of times it affects you later, a few generations later on, when you're already dead.
If it worked in the first place, but I could finish my PhD at only advanced science, the smallest part. And that's not even for years down the track when someone else, takes the next step, and all of a sudden, and then someone else, which is why I quite like it. It's quite it's satisfying to me because even if I don't make a huge difference, I've played my part. I've tried, I've helped, and you never know, maybe someone else builds on it. And before long, I've been part of a process that has, created so much more benefit to society than I could have ever imagined just solely on my own. And that's how a lot of things work, but that's what I do like about science. It's you're playing your role, but it's not for everyone. As much as I would like everyone to be able to at least partially think scientifically, I'm talking there in terms of the method, like the scientific method, more critical thinking style stuff, rather than I need everyone to be a physicist or to get a PhD in something. No, that's ridiculous. And I don't know any scientist who thinks that. I know of a few who think there should be more people with science degrees, but even I'm like, I don't think we need more. We just need, I guess, greater awareness. That would.
Okay. Do you ever have to, in your, I don't know if it happens if you field of study, but do you ever come up with against younger creationists in your laser field of study or greenhouse stuff?
Not really. And Australia doesn't have a lot of young Earth creationists. There's not many around, and within physics, you're not. It's actually there's a few. I've worked with a lot of religious scientists, but so far none of them have been young Earth creationists, and I've actually worked really well with them. I've had some really interesting discussions with others too, and we do really good science. I've got, friends, like I've worked with very, very devout Christians and Muslims and a few other faiths. You don't tend to always talk about it in science because it's, for the most part, it doesn't affect the science we're doing. We do science, and if they have their beliefs, but they're still a good scientist, I'm going to support them as a scientist.
Yeah.
On here, I'm not going to debate with them, and if I do, it's out of interest. It's more out of like I have any, and I've had lovely conversations. But yes, I know that the young Earth creationists though are very anti-scientific, and that's where I draw the line. I only have a problem when someone becomes anti-scientific, and that's when you do.
Like you sent, I think you sent yours our way, unfortunately, near where I live.
Oh yeah. We sent you Ken Ham, but we don't want him back. Ray Comfort is not ours though. He's a Kiwi. He's not an Australian.
His museum is literally 1 hour away from where I live.
Oh, fun times.
Yeah.
That it's quite the joke of a building.
I live in Southwest Ohio, so it's like right about an hour away from the Kentucky border.
Yes, although I can guarantee not one of their scientists will give you a nice definition for a laser if you ask them, although lasers don't tend to have as much to do with the age of the Earth. I mean, astronomy does, but I'm not an astronomer. I work in an astrophotonics group, but I don't tend to work in astrophotonics, though some of my projects have a really, really big overlap with astronomy applications. And whilst this gas detection wouldn't work in astronomy, another area I'm about to start looks at gas detection for columns, so looking ahead. And it's like, is there methane in front of me rather than is there methane at this point that I'm detecting? And that can also be used in astronomy. If I want to look for chemical signatures on, say, exoplanets, that's the sort of thing you do. But I can take that same technology and go, is there methane in front of me? And how much of it is there? So that's what this.
Astronomy lasers, can it show you the size of a star or planet from the distance?
Oh, that's actually a good question. I'm not sure. I've got to think about that one. I think in theory you can, because you can use like radio, like you can use lasers to do range finding. Although I know they tend to use radio signals for that, say to Mars. I think it would be less useful for more distant planets. Okay. You tend to use things that are known as standard candles, or if it's closer. So I think it's about 100 million light years or a million light years. Sorry, this is not really my area. You can use parallax error, which is the equivalent of if I hold my finger out or you hold your finger out in front of you, you close one eye and then you switch, your finger seems to move. And based on how far it seems to move, you can figure out how far away it is. So you can do that for closer objects, and that's easier than anything, I think, the laser. But yeah, it's a good question.
If you ever ask the laser astronomer, he answers you, comment down below.
Although I'm seeing the question you've put up there, could you use to determine the age of the Earth? I guess I can't think of an easy way. You could potentially, I mean, synchrotrons are the modern day X-ray lasers that basically came out of that whole Project Excalibur era, but they don't use nukes. They use a particle accelerator for electrons and then use magnets to wobble the electrons, and that generates X-ray lasers. Essentially, it's really cool because if you have a charge and you move it around, you accelerate it, you generate radiation, and so you can control that. And so with those, you can study crystal structure and the structure of materials. So maybe there's a way to incorporate that into ages, but it's less likely.
All right.
I think it's not going to do a lot, which is why my field is not going to get much pushback. I'm more likely to get pushback when they start denying climate change, which a lot of them tend to.
No, that would be your thing. Like most YECers don't think climate change is happening, or
a lot of non-YECers do too. So yeah,
they also don't think either it's not happening or it's not that big of a deal. Because
yes, I've come across a lot of both who aren't young Earth creationists. So it's just like climate change deniers in general. It can be a bit of a problem because
I think my favorite one is God's going to destroy the Earth anyways pretty soon. So what's the point?
But no, we're on the planet now. Look after it. It doesn't mean we get to destroy it first. It doesn't make a lot of sense, but oh well.
So what do you like to? What interests you? What other interests do you have besides lasers and climate studies?
So, I mean, that's my PhD, but I mean, astronomy in general, I find really fun, really, really cool and interesting and fascinating. I also really do like my history. So whether that's like sort of paleontology and like history of the planet or history, ancient and modern history, I tend to like, World War I, World War II a lot, but I also, one of my favorite areas is like Meso and South America, pre-Columbian. So looking at the ancient and the medieval Mayan periods, the Olmecs who go back even further, or if you want to look at the medievals, like right up till the Spanish arriving civilizations, such as the Aztecs and the Incas, I find that fascinating too. And as I said, there a couple of times lasers have been used in that, and I was like, yay, lasers! It's always, I said, you can use lasers everywhere. So that's why those examples came to mind. But yeah, World War I and II, you don't see any lasers yet because they hadn't been invented. You got to get to 1960s before you start to see them, which is also one of the things people have said about the moon landings, how we know they're not faked because the shadows are parallel. And people are like, well, you could use a laser, but yeah, not in those days. They couldn't build them. Not to do what they did. Plus, you wouldn't get the effects there. Lasers don't look like that.
Yeah, the fake moon landing and the flat earthers are a strange bunch too.
Yes, there's a lot of pseudo and anti-science out there, and but I find them all fascinating.
Can lasers be? Speaking of that, can lasers prove that the Earth is round, not flat?
Yes, it does it. They do them really easily. You just need to fire lasers at each other over a distance. Make sure you take refraction into account, although that does annoy a lot of flat earthers. But lasers can travel a lot further than most light can. But you can actually fire them, and based on the angles, let's say you set up like 3 points around the Earth, as long as they're far enough apart, you map out the differences in the angles. You can do this. You can basically map the surface and see the curve, or you can fire the lasers at each other and detect the angle. So I've got the two other states. Let's say I'm one station. I've got my lasers, and then there's two others out that way. I can fire them out. We add all the angle sums up for the triangle. If you're on a flat surface, it's 180 degrees. If you're on a curved surface, it isn't 180 degrees because a curved triangle starts to change that angle sum. So you can actually tell whether the Earth's flat or not from that one. And you can tell exactly how curved or not it is depending on the area, which is really fascinating because that also somehow, this is such a tangent, leads into whether the universe is infinite. Or at least similar way you could potentially tell if the universe was curved. You do the same thing. You look at other objects and try and tell whether it's curving. But as far as we can tell, it doesn't seem to be. But we could have the same problem as the flat earthers, that what we're looking at is too small. So we're not looking at a big enough area to see the curve.
Okay. So sorry about that. So you like using like lasers for almost like triangulation of things.
Yeah, so you can use it, and when you build the triangles, you can look at those angles and how they, and you can basically use them to directly measure curve. A little harder in astronomy. In that case, you're not really using lasers. You're just looking at lining up different points and mapping them out visually. But at least for the Earth,
we don't know, or do we know that again, this is an astronomy question. You probably don't know this. Like, is the universe flat, like a flat disk, or is it like layered up, like different places, like a 3D?
That's the big question. It appears to be flat, but most astronomers will be very careful in that they'll use wording like that it looks flat, but that doesn't mean it is flat. At this stage, there are some things that would make more sense either way. And so whilst, as I said, it might appear flat, it could just be because we're not able to look at a big enough area to see the curve. It could be so slowly curving that it's just not detectable, which is cool and slightly scary at the same time, that we may not be able to detect what the universe is really like. But that's also the thing I like about science. We always need more questions. We need more things to solve.
In a few hundred years, that'll be the next big debate: flat universes versus curved universes.
He already is. It's already a debate, but see, the scientists debate much cleaner than, or generally speaking, much cleaner than the flat earthers do. It's because we can't yet know that answer, and there are arguments either way that it's hard to tell. And there are, as I said, there is some evidence to suggest it might be curved, and we just can't see it. I've even heard proper astronomers and cosmologists in this case who have given arguments that at least point to the fact that there could potentially be a multiverse and the universe is still curved. They're not, but again, at this stage, there's not enough to definitively say what it is.
Okay, but
and that's kind of where I sit.
Cool, but of course, it's more actual debater than between a globe earther and a flat earther.
Yeah, this time it's actually that we don't have enough information, so it is people who are trying to do the science, and we can't yet draw a definitive conclusion. So they're trying to figure out ways that we can answer those questions. So it's not the easiest thing to do, but hopefully we get there one day. That'll be a cool discovery when if we have enough evidence to fairly definitively conclude the shape of the universe. That'd be quite the nice fundamental question about what it's like.
Besides flat Earth flat, we also know that the Earth is not the center of the galaxy or universe. It go around the sun.
We're right out we're on the edge of both.
But could lasers be proven that we use lasers to prove that we're not the center of the universe?
Unfortunately not, because as I mentioned, so it's known as beam divergence. They spread out, okay. So you have a very limited range. And when you're trying to talk about astronomical distances like that to see the whole universe, unfortunately, the lasers spread out and just the beam just becomes too weak after a while. There's not it's spread out. It's like trying to see a light bulb from another planet. You're not going to. And unfortunately, that's what we run into. As I said, you can direct them further than a regular light bulb, but not enough to answer those questions. As much as I wish I could say my area could tell us, what the universe is fundamentally is, it is but a dream.
Apparently, we either have a fake troll in comments, a flat earther, or a real one.
So show me Sasquatch. That sounds like a bit of a troll name anyway. Spinning balls, water always finds level. Well, tides. Also, if you put something in free fall, water doesn't flatten. It actually forms a sphere. And same in space stations. So No, water will find its level when you put it under gravity, which shows the Earth is round as well. There we go.
So, so what do you do for fun what do you do for fun when you're not doing your studying and lasers and your college stuff?
At the moment, I'm hiding from COVID, but apart from that, I do enjoy going climbing. I like my rock climbing because it's like a sport where you got to problem solve, and it's a problem solving that kind of gets your brain away from everyday activities. Or I'll also, well, I make videos, so that's part of what I do. And as I said, I want to, if I have the time, I'll get video out. I'm pretty much done it. Even the thumbnail's ready. I just sort of need to do last minute checks and then release it. And it's I've already mentioned what it is. Oh, did I? I did already. Did I mention? No, that was only on the channel. Maybe.
Yeah.
Anyway, it's on the Fisher Space Pen.
Okay.
So it's astronomy related to an extent. So we got that, but I don't mind playing occasional video game. Sometimes too much, but I like my strategy games on that. Or I'm a bit rusty at the moment, but I can also do card tricks, close up card magic. I did do a video, although I made it unlisted because it got no views. So, but I did try making a video on that. I find it quite fascinating, but I understand it's not everyone's cup of tea. So, what about yourself?
Well, right now my personal goal is I'm trying to write a fantasy fictional book. Not as fantasy as some of the YC books out there, but actual proof to be fantasy books, And
that would be cool.
And then I also like when it's actually warm outside, I like to ride my bike places. I've gone 18 miles on one trip one time on my bike.
Very nice. I'm doing the conversions in my head. I can do miles at least. Just don't ask me to do temperature conversions quickly.
Yeah.
But that's good. So
yeah,
is it nice weather for you for riding?
Not right now. It's like 15 degrees. But yeah, in the spring, summertime, when it's not too hot, like anywhere between 60 to 70, 80, 68 degrees, I can go. We have like lots of bike trails around here.
Yeah, that's nice. You got a few walking tracks around where I am, and people ride bikes on the street. But I don't mind the occasional hike either. And we're in summer, so we're kind of the opposite. That we're getting some days where it's too hot to comfortably do those things, but it's also really muggy. It's not having a very mild, wet summer because of the weather cycles at the moment here. So it's cool summer days and really hot, muggy nights, which is oh well.
Yeah. I also like. Besides that, I just play video games. If I remember to record and edit them, and I do this podcast.
Oh, cool! I should have a look at that too. So I do. What sort of games you play?
Mostly, right now, mostly RPGs and visual novels. Like, I know you're talking about like the visual RPGs, like the Kingdom Hearts series, where they take Disney and Final Fantasy and put them in a blender together. Cool. And then
you have some nice storylines for those videos then.
Yeah, visual novels, like my favorite right now is Danganronpa. It's a murder mystery with killer teddy bear locking kids in a school to kill each other or on an island or whatever. And then there's Steins Gate, which was about a time traveling microwave. You should microwave itself for time travel. And then the last one was the Phoenix Wright series about lawyers. And then meanwhile,
yes, I'm keeping an eye on the chat. If you want, I'm happy to address a point if our flat earther here wants to try and make one.
Sure.
You've got the opportunity to ask a physicist, and I'm almost a doctor. I am also watching this on YouTube, so you can, if you tag me, I'll see it. How about you give us your best evidence for the Earth being flat, if that is in case your viewpoint, or you say what it is and give us the best argument, and you can get my opinion on that, because I've never actually heard a reasonable argument that even comes close to even if it was correct, showing the Earth was flat.
Okay, so while we're waiting for that question,
yeah,
the other person I know studying for their PhD right now, Erica, is teaching classes. Are you a teacher too, or are you just a student?
Yeah, so I'm not a student in the traditional sense that I attend lectures and sit exams, though my days of that are done now. I've done many years of that, but I'm now researching. And yes, I also do teach sort of on the side as casual, because that's really, really common for most PhD students. And I know that's more than just Australia will teach. I like teaching chemistry labs, even though I'm a physicist, because I have that background. And I'll teach high school students too. I enjoy it. It's good fun. So that's cool. Is that your best? That's not evidence for the Earth being flat, because we can't see anything below the curve. I've already mentioned the lasers. Like, you can fire lasers and basically see whether the Earth is curved or not. You can make a direct measurement with that. So we can't. And the only cases that seem to be the exception are refraction. And I deal with light matter interactions. I am very, very, very familiar with refraction and how it works. And so depending on the conditions, because it's a density related thing, or at least because the more dense an object, the higher refractive index, so the more refraction you'll get. That will also determine, because it can slightly bend the laser around, and that can make it seem like you're seeing things that would otherwise be behind the curve. But apart from that, we can calculate exactly how far we can see those things, and it matches all the calculations for that. I'm yet to see a flat earther get it correct. So there we go. But I think we might leave our troll there. So
no, he is. I am, but no, he is not. He's an Australian citizen.
Yes. I'm apparently in the land that doesn't exist. So that's a running joke I've got on other channels, that Australia doesn't exist.
That's my joke I was going to make about COVID. Hey, you're the ultimate isolationist thing. You're on an island, a big island. So
I mean, we were, but in the last few months, we've basically had COVID run right through us. Was that directed at our troll or any of us?
I'm not sure.
Also, I can see that on Facebook. Yeah. Okay. Well, I'm happy to answer that. I just want to check if that's me, or whether that's meant to be directed at our troll thingy. Okay. I do want to address one thing. Never wore a face diaper. If you're wearing a diaper on your face, you're doing it wrong. But the masks work. Please, everybody, don't listen to this guy. They're helpful. They don't reduce your oxygen or increase your CO2 blood concentration. We know that. We can measure that pretty directly. Oxygen monitors, stick them on your finger and put a mask on. That's the easiest tip.
I was thinking about the mask. They say I can't breathe in the mask. And how they can you can still breathe in the mask, and how they can prevent viruses. How big a virus is compared to a CO2 molecule or whatever. Even though viruses are small, molecules are a lot smaller than viruses.
Yes, and the thing is that viruses don't come out as individual viral particles. They come out in liquid droplets, in basically aerosols. And those droplets are even bigger, and they get caught in the mask. That's why masks become less effective over time, and if they get wet. So you need to make sure that you're changing them up, or if you've got reusable ones, you don't use them for too long and you wash them in between. But they are the most effective prevention method outside of like physically keeping away from people that we've got. If you have to get close to people, they're the best thing to start, particularly for COVID. If you're looking at like the Omicron variant, the main receptors, so the place that is most likely the easiest place for you to actually catch it are in your nose. So make sure the mask covers your mouth and your nose, and that depending on the level of the mask will protect you and others. But and of course, here we go, because I don't apparently believe in a flat earth, or that I also follow the science on COVID. Apparently that means we don't believe in a God somehow. I don't know how that follows. And frankly, today, that's not something I tend to debate. It's not something I do on the internet. I like science.
Yeah.
And I think a lot of people do, because, I mean, who doesn't want to talk about lasers?
Definitely. Yeah. I hate that black and not get into it, but I hate that black and white. You're fully this or you're fully that.
Yeah, and as I said earlier, I'm not here to debate that. I when I say here, I mean on YouTube in general, because as I said, I have worked alongside with a lot of people with different views to me on that, and we've done really good science. As long as you're following the evidence, I don't care. And I do want people to disagree with me, because that helps me.
Yeah.
If realize if I'm
was
wrong.
like a isolationist think tank, you never learn anything new.
Yeah, the fact if I'm not making mistakes, I'm not learning, and I do like that. And so if someone tells me I'm wrong, even if it turns out I never actually end up agreeing with that, it still gets me to think more on my point of view, and that's useful. So it can do that.
Yeah.
But
so
that's fascinating.
Yeah, on a more interesting topic, down in the planet doesn't exist right now. It's summer, right? Because of the Earth tilt thing.
Mm-hmm. Nice and warm here in Sydney.
Oh,
the day it's not as warm as a lot of our summer days. We're still below 30 degrees Celsius. So we're about 70, maybe a bit above 70 degrees Fahrenheit, which is not particularly warm, or at least in my room it is. But it's the humidity is quite high.
Yeah,
it'll get a bit warmer outside.
Here's 22 below 22 Fahrenheit.
I don't like the cold. I'm happy I'm here.
I don't know how there's a Celsius conversion on this phone app, but yeah. But yeah, all I know about the Celsius conversion Fahrenheit is 0 and 32, 212 and 100, maybe 3798.
Yeah, I know that 70 is around low 20s sort of thing, and I think we're looking 40 is about 110 Fahrenheit, if I've got that correct. But I know that at rough like cooking temperatures, it's roughly double, very roughly, but it is. So
I think that's all the questions I have. I can think of.
Mm-hmm.
Anybody in chat have any questions? Any like real questions, not stupid questions? I don't say that stupid. I don't say that stupid questions, but
honest questions, maybe. Yeah. Because I like doing that. A lot of my regular shows I'm starting to do, or at least semi-regular, I like to have huge Q&A portions where it's just ask me anything about science, because those can be fascinating, because you end up going places you never expected, and you get to have that interaction where you find out what people are interested in.
So anything come up on your channel that you want to advertise?
I'm hoping to release a video later today, as I kind of hinted at earlier, or well, probably more than hinted by now, but on the Fisher space pen. So did the Russians bring a pencil when the Americans spent millions of dollars developing a pen that worked in space? Nope. But what did actually happen? Well, that's what I want to answer, and I'll explain how the space pen works, and that'll be coming up. And then I will be in kind of few weeks sort of time period be doing other videos where I'm getting different scientists on or different people with experts in other areas, so that I can cover a more broad range of topics. I'll probably be doing a weather one, and I'll be doing a few probably with people like Brainbug at some point. We've discussed it, though nothing's set in stone for those yet.
Yeah, Brainbug was my guest last week, I think, or maybe 2 weeks ago.
We did dinosaurs in movies and what they should look like. That was a cool show. I enjoyed that.
Yeah, like last week we talked. I forget we talked about. We talked about last week. Me and Brainbug were on. We talked about wings, about the wings of insects and tetrapods like pterosaurs, birds, and bats.
Oh, that's cool. I do like my kind of evolutionary history. It's fascinating.
Yeah, how the poor tetrapods had to modify their arms to fly, but the insects were like, screw that. We're gonna make our own.
Yeah, we'll just get extra wings, and everything else is like, oh.
Yeah.
Oh well. I kind of wish I had wings sometime.
Yeah, so sometimes do I. I don't know if he's still in chat or not, but if Venerable Bede, he's going to be on my channel next week to talk about Henry VII of England, the father of the Tudor branch of the family tree.
Oh, that'll be. I do like my history, so if I'm around, I'll try and tune in for that. So yeah.
Yeah, if your Australian time zone will allow it.
Well, it's also weekends, so it can be a bit hard depending on what I'm doing during the day as to whether I can jump on. But hopefully I can catch a bit of that, even if I have to watch it afterwards.
Well, it looks like there's no questions at all. So, all right. So, thanks for being on here.
Thanks for having me on.
You have anything that you say at the end of your streams or anything? Like, you have your catchphrase or anything?
Yes. Be like a proton and stay positive.
Nice. As I always say, never stop learning. Enjoy the randomness. I'll see you next time.